Hello everyone and welcome to Instant Biology by Dr. Nilab. I am with you again with a very important lecture, and this lecture is purely devoted to the numerical sessions, the numerical knockout sessions that we have been conducting in the past as well. In today's lecture I would be focusing upon the bioprocess engineering related PYQs. Why I am taking suddenly bioprocess engineering, because you might be knowing that the GATE biotechnology exam is around the corner, and a lot of students have requested me to take up some bioprocess engineering questions. So in this particular lecture I have chosen some very important questions that I feel would be important or can be important in the upcoming GATE biotechnology examination. So in this lecture I would be telling you about what things you should keep in mind and how you should be aiming at solving questions related to bioprocess engineering. So without much ado, let us just quickly switch over to the first question that I have chosen for this numerical knockout session. So the first question over here that you can see on your screen is: consider a scale up of fungal fermentation. Now this clearly indicates that the question that we are looking over here is a scale up question. Now scaling up is a very important concept and you should keep it in mind for revision purposes, because a lot of questions have been asked from here. Scaling up of a fungal fermentation from a 20-liter model type to a 20,000-liter prototype stirred tank reactor. Now in the first line itself they have mentioned that there are two types of fermenter. Now the first type of fermenter is your model type of fermenter, and what has been given in this model type, the volume has been given, and they are saying that the model type fermenter volume is 20 liter. Okay, now so since there are two types of fermenters, model type fermenter and a prototype fermenter, so I am going to represent one for the model type and two for the prototype fermenter. So in this case, since we are dealing with the volume, so I'm going to just write down V1 in case of model type. Now the second thing that is given is the volume for the prototype. So prototype fermenter volume has been given as 20,000 liters. 20,000 liters. So let me just consider that the volume over here is V2. Okay. Now the model type and prototype have the same aspect ratio. That means the geometrical things are same, and the impeller speed in the model type is 500 rpm. That means, see, the impeller speed has been given over here. This is a way of representation. That means they write impeller speed, but they are implying about the impeller frequency. Why am I saying impeller frequency? Because you can see that the rotation per minute has been given. So rotation per minute is actually not speed, it is actually a frequency of the impeller. So we can just quickly write down that the model type impeller frequency is equals to 500 rpm, and I can write it down as Ni1, right? Because Ni is the notation for the impeller frequency. So Ni1 I have written down for model type. And what are they asking? They are asking the impeller speed in the prototype reactor, and that too that should be given in rpm. So prototype impeller frequency we have to find out. We do not know this, so that means we are not aware about Ni2. This is to be calculated for this particular question. Now one important aspect that I would want to bring to your notice, because this is going to be very important in other questions also. Remember that there is a very important relationship between the volume and the diameter of a fermenter. Now you already know, you would be knowing that volume of a fermenter is represented as pi r square h, and in general the height of the fermenter can be represented in terms of the diameter. So I can just write it down as 2d. So when I keep this value for height in this equation number 1, then what will we get? Pi r square into 2d. And we also know that the diameter is actually twice of radius. So what we can do is pi r square into 2 into 2r. We can write it like this also. So what we would be getting is, so pi r, this r will be can be joined over here to pi r cube into 4, or that means 4 pi r cube. This means that volume, because we are actually calculating volume only, so volume is directly proportional to r cube. This can be implied, or in other words, since radius volume is directly proportional to radius cube, we can also imply that volume would be directly proportional to the diameter cube also. We can also imply that the volume is directly proportional to the diameter cube also. I can write just over here. So volume is directly proportional to the diameter cube. Diameter cube, di cube. Okay. So volume is directly proportional to the diameter cube, diameter of the diameter cube. So this is again, I believe you would have got a clear idea about this. Now, so now let me just quickly move to the calculation portion of the diameter, since we are not aware about the diameter of the impeller. So since I have just calculated that the volume V1 upon V2, since we just found out that the volume is proportional to the diameter, so V1 upon V2 is equals to di1 upon di2, di1 upon di2 whole cube, right? So because volume was directly proportional to d cube, that is why I have written this. Now, since you already know that volumes have been given, so implying this, volume has been given. So volume of the fermenter first was 20 liter divided by 20,000 is equals to di1 upon di2 whole cube. Now what I can do is I can just quickly make a cube root. 20 upon 20,000, this would be equal to di1 upon di2, and in this way we can just quickly solve this, right? So what you would be getting is that di1 upon di2 is equals to 1 upon 10, right? So this is what you would be achieving. That means we are aware that the diameter of basically the impeller would be the ratio of the diameters of the impeller would be 1 by 10. Now, since they are saying that the impeller tip speed is constant, if you just check out this question, then they have mentioned that scaling up criteria is constant shear. Now when you are applying constant shear, then obviously that the impeller tip speed remains constant. I believe you would be knowing that when you are applying the constant shear aspect, there are different aspects in the scaling up. There are different criterias at which the scaling up can be performed. One such criteria is constant shear. In case of constant shear, we actually imply that we are having the constant impeller tip speed. So in this case, the constant impeller tip speed, we can calculate the general formula for constant impeller tip speed is Ni1 upon Ni2 is equals to di2 upon di1. So this is the scaling up criteria or scaling up formula. I believe you would be knowing this, and I'm just putting my values over here. So the value for Ni1 has been given because the impeller frequency for the smaller fermenter or the model type fermenter was given as 50 rpm upon Ni2 we have to calculate. So I'm just writing Ni2 over here. di2 by di1, the ratio we can just reverse this. di2 by di1 is equals to 10 upon 1 like this, and in this way Ni2 yeah, sorry, the Ni1 was given as 500 rpm. Sorry, I just wrote it 50 rpm. So it was 500 rpm, and so therefore Ni2 can be calculated as 500 upon 10, and this would be calculating as 50 rpm. So this is my speed. Yes, Ni2 comes out to be 50 rpm. So this, in this way we can find out, or we can calculate the first question. I believe you would have got a clear understanding out of this. Now let me move on to the second question on your screen. So this is your second question. Now, decimal reduction time of bacterial spores is 23 minutes. Okay. Now this is a question devoted to decimal reduction time. So decimal reduction time, or D value, of a bacterial spore is 23 minutes. So let me just write down the D value is equals to 23 minutes at 121 degrees centigrade, and the death kinetics follow the first order reaction kinetics. Of course, we know that whenever you are doing the sterilization, basically it will follow the first order reaction kinetics. 1 liter medium containing 10 to the power 5 spores per ml. Okay, so 1 liter medium containing 10 to the power 5 spores per ml was sterilized for 10 minutes at 121 degrees centigrade. So there are couple of things that you need to remember over here, because they have given you the spore value 10 to the power 5 spores per ml is the concentration that they have given, and the total volume of the media is 1 liter. So they have given you that for every ml, 1 ml, 10 to the power 5 spores are present. But since you have to consider the spores that are present inside the entire volume of the fermenter, let me just quickly just draw it over here. Suppose this is a fermenter. Okay, this is a fermenter. Let me just a rough drawing. So the volume inside the fermenter is, let us say, 1 liter, and they have given you that per ml the spores concentration is 10 to the power 5. So I will have to convert it into 1 liter. That means 1 liter would be equal to how many ml? 10 to the power 3 ml. So if you want to convert it into a per liter measure, so 10 to the power 5 into 10 to the power 3, it will be giving you 10 to the power 8 spores in the, or let me just quickly, 10 to the power 8 spores. I should write it over here because you might not be able to see it. Let me just transfer it over here. So this would be 10 to the power 5 into 10 to the power 3 is equals to 10 to the power 8 spores in 1 liter medium. So this is what we are having. So this is another value that we have got. This is another value that we had got. And one more thing is that the time for sterilization has been given to us. Time is equals to 10 minutes. This is what we have given, that we have been given. The number of spores in the medium after sterilization, assuming destruction of spores in heating and cooling period is negligible, will be 10 to the, this value has been given. Now you might be knowing the formula for decimal reduction time. So the D value, or the decimal reduction time, can be calculated as 2.303 upon K. K is the constant, you might be knowing about that. So D value in this case has already been given to us. Let me just quickly solve this entire equation. So D value is 23 minutes is equals to 2.303 upon K, and in this way the K can be calculated. So K is equals to 2.303 upon 23. K value is equals to 2.303 upon 23, and in this way you can just solve it. Roughly it will be coming out to be 1 by 10 is equals to 0.1. This would be my K value. Now coming to the next thing that you might be knowing, that we can basically use a formula, and we can just use the logarithmic formula for the first order reaction kinetics, and then we can find out that what would be the final concentration of the spores. So let me just quickly write down the formula. Log, or rather ln, I should write it down over here, ln n0 upon nt is equals to kt. This is the formula that we should be knowing. Now, in this formula, I am aware about the k value, since we just calculated k value. I am aware about the t value. I am aware about the original NO value, and I have to find out the NT value. This is what we have to calculate. Let me just quickly convert this ln into the log. You would be knowing that if you want to convert ln into log, you just have to multiply it by 2.303. So 2.303 log, and n0 we already know it is 10 to the power 8 upon nt we are not aware. Nt is equals to k is equals to 0.1 and time was given as 10. Now, so we can quickly calculate it as 2.303 and log 10 to the power 8 minus log nt is equals to, and this would be equal to 1. So I can continue it over here. So 2.303 into 8 minus log nt is equals to 1. So next is, then you can 8 minus log nt is equals to 1 by 2.303 and minus log nt, you can minus log nt is equals to 1 upon 2.303 minus 8. And if you are solving this, what you would be getting is this would be 7.56. This, if you solve this, it would be coming out to be 7.56, and anti-log of 7.56, anti-log of, since you have to calculate nt, then you will have to take the anti-log for 7.56. So I'm just writing down over here. Just let me just take one additional page. So anti-log of 7.56, if you take it out, then you would be getting the value for nt, and this would be coming out to be 3.6 into 10 to the power 7. So roughly, since the question says that you have to find out with respect to 10 to the power 7, so roughly you would be getting the answer as 3.6. Okay. So I believe this is clear to you. This is clear in your mind that how we can solve these type of questions. So this was an important question. You should have this in mind. Now let us move on to another important question, and this question is related to the downstream processing concept DSP. And this basically, if I go into further detail, this process is devoted to the cross flow filtration process. Basically, it is a type of filtration that I'm aiming at. So in cross flow filtration process, this is clear that it is a downstream processing. Cross flow filtration process, the pressure drop delta P driving the fluid flow is 2 atmosphere. Now let me just quickly draw this diagram over here. So this is a cross flow filter. Let me just consider it like this. From here the liquid is entering, and from here the liquid is exiting. Let me just write it down that the initial pressure Pi is over here, the exit pressure is PO, and that is PO, and over here there is the permeate pressure or the filtrate pressure PP, or we can write it as PF as well. So in the cross flow filtration process, the pressure drop delta P has been given to us, delta P value has been given to us, and this is 2 atmosphere. The inlet feed pressure Pi 3, Pi is equals to 3, inlet feed pressure Pi is equals to 3. Now Pi, since that means this is given to us as 3 atmosphere, and the filtrate pressure is equal to atmospheric pressure. So filtrate pressure or permeate pressure is equals to 1 atmosphere. Why have I written 1 atmosphere? Because it is equal to the atmospheric pressure that they have mentioned. Atmospheric pressure is considered as 1 atmosphere. So these are the values that they have given, and they are asking you about the transmembrane pressure drop, TMP, delta TMP they are asking you. Okay, now first thing first, that the pressure drop can be calculated as, the pressure drop has been given as 2 atmosphere. The pressure drop is equals to Pi minus Po. This is the primary thing that we can do. So pressure drop has been given to us as 2 is equals to Pi has been given to us as 3 minus Po has been given to us as Po. So Po can be written as Po is equals to 3 minus 2 is equals to 1 atmosphere. That means the exit pressure over here is 1 atmosphere. Exit pressure over here is 1 atmosphere. Now, the next thing that we have to use is the formula for transmembrane pressure. Now, how can you calculate the formula, or what is the formula for transmembrane pressure? So, transmembrane pressure or delta TMP is equals to Pi plus Po upon 2 minus permeate pressure or filtrate pressure, whatever you want to write. So now we know the Pi value. Pi value we have been given 3 atmosphere is the Pi value 3. Po we just calculated now. Po was 1 atmosphere plus 1 upon 2 and minus Pp. That means the permeate pressure or filtrate pressure, this was given as 1 atmosphere. So we can just quickly write down as 1 over here. So if you calculate this, so 3 plus 1, 4 upon 2 minus 1, this will be 2 minus 1, and this will be equal to 1 atmosphere. So this is how you can calculate the cross-flow filtration process problems, and you can calculate the transmembrane pressure problems. Okay, so now let me just move on to the next question. Now this is a question that is related to the instrumentation process in bioprocess engineering. So a proportional controller is used to control the temperature of an autoclave from 60 degree to 130 degree. Now proportional controller basically is basically a device that is used to control the temperatures inside the bioprocess reactor. So from 60 degrees to 130 degrees, it is controlling the temperature of the autoclave, and proportional band setting of the controller is 25%. The proportional gain value is, now remember that the proportional gain can be mentioned as, proportional gain can be calculated as 100 divided by the proportional band settings. Proportional band setting, and this should be in percentage, since you are dividing you are putting it in denominator and numerator as 100. So proportional gain can be now finally calculated as 100 upon proportional band setting has been given to us as 25, so you can just divide it by 25, and this would be coming out to be 4. So this is the final proportional gain value that we are getting over here. So 4 is the answer. Now this was a simple question, and this is coming out from the instrumentation process. Now let us move on to the next question that we have. In a thin layer chromatography experiment using a silica gel plate. Now let me just quickly draw a silica gel plate for you so that you can understand the question better. So let us say that this is a silica gel plate. This is the mobile phase, like this, and let me just draw the solvent front. Now let us say that this is your solvent front. For the solvent front, I'm just writing SF, and let us say that the compound migration was, let us say that the compound migration was here. This is the compound migration. This has been given as 12.5, and the you see the migration of the solvent front was given as 18. So this was 18. This was 18. So now what we have to do is, you would be knowing that when you are putting a thin layer chromatography plate inside a solvent, then what happens is the solvent starts to rise up because of the capillarity force, and up till a certain limit the solvent front rises, and that is called as the distance that the solvent front is traveling. So over here that value has been given to us as 18, and you would be knowing that different components or different compounds that have to be separated are dissolved inside the solvent, and they travel to different distances depending upon their affinity towards the stationary phase or mobile phase. So I've taught all of this in my bioprocess engineering classes. So now let me just see what is being asked. So over here they are asking about the retention factor value. Now remember that retention factor or this is also mentioned as RF, it is equal to the distance traveled by the compound. Let us say that the distance traveled by the compound is over here 12.5 divided by the distance traveled by solvent front. Now this is a very simple concept. Now distance traveled by the compound has been given to us as 12.5, and the distance traveled by the solvent front is 18. So if you calculate this, the answer that you would be getting would be 0.694. This is the answer that you would be getting. So hopefully you would have got this clear idea, and this is a downstream processing question again. Now let us move on to the next question, and this would be the last question that I would be taking today. This is again a concept of sterilization, and a lot of questions have been asked from sterilization, and this question is basically on the concept of DEL. Now, so during sterilization, this is a linked question. There are two questions that have been asked on the given data only. So during sterilization of a fermentation medium in a given bioreactor, del heating is equals to 12.56, del cooling is equals to 7.48, and the total value of del for the whole process is del 52. So the del, what is the value for del holding? Now let us understand this. So first thing first, that del is a criteria to understand the sterilization. Now, so the del total comprises of del heating plus del holding plus del cooling. Okay, let me just explain it to you with the help of a concept. Let me just first of all put it in a box. This is an important formula that you should be remembering. So right, so whenever you are heating, whenever you are putting something inside the autoclave, what will happen? Initially the temperature will be rising. During the temperature rise, some bacteria or some pathogens would be killed. Then you would be holding the temperature at a particular point. At that temperature also some bacteria or some pathogens would be killed, and then again you would start lowering down the temperature, then again some bacteria would be killed. So del is giving you an estimate that what is the what number of bacteria or what number of pathogens are being killed at different processes. So del total, the entire del would be comprising of del heating plus del holding plus del cooling. Now in this process they have given you certain values, that del heating has been given to us as 12.56, and del cooling has been given to us as 7.48. So simply we can just find out the value for del holding, because del total has also been given to us is equals to 52. Now we can just put in 52 is equals to 12.56 plus 7.48 plus del holding, and in this way we can find out the value for del holding as the del holding final value would be 31.96. You can just subtract 52 minus 12.56 minus 7.48, and this would be coming out to be 31.96. Now another important question that has been asked over here is, what is the holding period in minutes at a K value of 3.36 per minute? So remember, there is another formula for del, and del is equals to ln n0 by nt, or you can also write it as kt. Del value can also be written as ln n0 by nt is equals to kt. Now since we are only talking about the holding period, so del holding value has been given to us as 31.96. We just calculated it, so we can write it as 31.96 is equals to k into t, k into t 3.36, right? So the value for k can be calculated as 31.96 upon 3.36, and in this way you can calculate and find out the value to be around 9.5 somewhere. So in this, del holding will be 31.96 and this over here would be 9.5. So these are some of the important questions that I think of bioprocess engineering. Soon we would be launching our GAT-B batch in the upcoming in a couple of days, and I will be informing it to you on the YouTube channel and in the Telegram group as well. So stay tuned. So those of you who are looking forward to the GAT-B preparations, this batch would be essentially very, very useful for you. So thank you so much and have a good day.